6 times the true output with 0 quality loss. That's the claim of freshly merged DFlash to Lamma.cpp for Qwen 3.6 family. So today we are doing 3 things. First, I will break down how it actually pulls that off. Second, we'll deploy it on our own PC in basically one click with Lamma.cpp and Docker. Because claims are cheap, the third thing we'll do is benchmark it if it's truly lossless. I'm Łukasz, I'm lead Gen AI engineer that specializes in inference optimization, and DFlash just looked like this. So here we can see the autoregressive Qwen 3 in 8 billion version. It achieved 48 tokens per second. Then we have block-diffusion with 97 and it's lossy. Then we have EAGLE-3 that achieved 114, that is lossless. And then DFlash, which achieve over 400 tokens per second. Lossless means that it don't lose the quality. So we'll look at this claim now through short introduction how it actually works. So let's start with numbers because they are the reasons we are here. As we can see on the blue we have the DFlash speedups compared to Eagle and then the baseline on different benchmarks, MAV 500, GSM 8K and LiveCodeBench. And as we can see, this was the state of the art. And now we have multiple of this. And we'll find out later how it was achieved. So let's look at some quick recap of why decoding is slow in the classic LLM models. So as we can see here, we have autoregressive 1 token per forward pass. And this is visualization how classic LLMs work. So today we will explain speculative, decoding, diffusion, and DFlash. So it's one by one. Why it's one by one? Because the companies that serve you like models like ChatGPT or Cloud, they have thousands of users. So they basically batch you. So you are batched with like thousands of users. We go into more specifics into my last few videos. So they will be somewhere around. So you can check them. About MTP, we do full explanation of how the full prefill decode works. But the short story is that on typical GPU of person who is at home, we don't even utilize the GPU as much because mostly it waits for the data to load. So here, for example, verifying 16 tokens in one pass costs almost the same wall clock as generating one. So we pay for bandwidth, not flops. And that's the whole foundation of speculative decoding, because it would be pretty nice if we could generate all of those tokens in one pass, because then it will be faster and this compute will be nearly fully utilized. So we'll not have resources hanging, not doing thing for us. So now let's look at the speculative decoding in 30 seconds, because this was also explained in the MTP video. So we have a small drafter that takes guesses at a block. It's like canvas. And here we see the capital of Spain is Madrid. So the draft model choose 6 tokens, and we can see that this get accepted and this got not accepted. And the difference is that like here, if one token is not getting accepted, then all of the rest are useless because we discard them. And then we will correct them. So the output, then the target model will add the token that was false. So the capital of France, for example, will be added. And then we do another draft. So we typically define this window of like 6 tokens. So the math is simple here. The per token latency is drafting time plus verification time divided by tau, which is average number of tokens accepted. So we have 2 levers to make drafting cheaper or make drafts better, so more get accepted. And every method is a different trade-off between these two. And issue with existing methods are quite nicely visible at EAGLE-3. So EAGLE-3 drafts auto-regressively. So drafting cost grows with every token we speculate. Why? Because even though the drafter model is smaller and it's much faster than the big one that accepts the tokens, because we do it one by one, then we'll be constantly waiting. And there is also another issue that was visualized. So the drafting costs grows linearly with every speculated token. So to keep it cheap, the drafter is single transformer basically. And one layer model isn't a great language model. It accepts around 3 tokens per cycle. And pushing the speculative budget higher barely helps because acceptance saturates while the cost keep climbing. So error compounds too, yeah, because one wrong token, that we showed before, kills everything behind it. And that's the wall to break it. We need a drafter where the cost is not scaling with the number of drafted tokens, which is exactly what diffusion models could give you. And we talk about diffusion with Llama.cpp, yeah? So this is like all mixing of the ideas that were explained before. We don't want autoregressive in the drafter, so we'll use the diffusion. Now to quickly show you how diffusion works, because I have like full video regarding how it exactly works, we'll use a short example with comparison. So here we have autoregressive drafter and the block-diffusion drafter. So we have the mask spots at the beginning, so that's what the drafter will predict, and then it predicts the tokens. So as we can see here, I will replay it. We filled it one by one, and for diffusion we fill all of them immediately, yeah? And then the green ones are the accepted tokens, so that's the tokens that were accepted by the bigger model, which means they are correct, yeah? And we use bigger model because that's when we have lossless quality, because if the big model accepts the token, that means that we have the same quality as if it would generate it. At least that's the idea. And let's do a quick replay. So as we can see, we generate tokens, and if there is any failure, then we need to subtract everything after it. And here, as we can see, we have also many failures, but because we can generate so much tokens quickly, we generate 108 tokens compared to 21 with the same number of steps. And as you can see here, we have much less mask slot on autoregressive drafter than the DFlash, and there is a reason for it. How does the drafter know what to guess? As the big model reads the prompt, its inner layers already form a strong hatch about the next few words, and the trick is where we hand it over. In the EAGLE case, we handed it once at the beginning, so the knowledge basically was getting more shallow the more layers it goes, because we lose the signal from this hunch. So we can say that the drafter is then getting faded and it stays shallow. Then in the DFlash, we pin this knowledge to every layer. So as the layers keep increasing, we still keep the memory, so the drafter can increase. And this could be visualized here. So typically the drafters are around 4 for MTP and so on. But for this, we can have much higher value because we are still keeping the hunch about the new words that we will predict. So here's a punchline why this mechanism matters. And we have same acceptance and double the speed. And let's look. So as we can see in MTP, we draft 1 token per forward pass. So to draft 7 tokens, we need 7 passes. So that's, of course, is slow. And DFlash proposed a new block. So we propose block of 16 tokens at once, and they all get generated, the full block. So we do it in one pass. So a diffusion drafter cost barely change with the block size. So DFlash can propose much bigger blocks, up to 16, 40, for almost the same price as just one pass in the classic autoregressive MTP. Now, what it buys us? Both end up accepting the same number of tokens per cycle. We can see the value of tau here, 6.7 or 7.3, and they are closely tied, let's say. So the acceptance isn't the difference. The difference is the time. MTP paid 7 times for sequential passes, and DFlash paid only once. And we have the same tokens on the output, so at the fraction of the costs. And that's why the DFlash is much better than the classic MTP. But that's enough theory. Now let's run it. Okay guys, so as promised, here with one click you can deploy the Lamma.cpp server with DFlash model. Everything is configured here. As you can see, we have context. The interesting part is that you need to use this drafter because it's after merge. And as you can see, there is difference between the accuracy of GGUF here, but this is okay. This is something that you can play with to get more accuracy on drafter because it's less quantized, or if you want to have it faster. And we can define the draft tokens here. And if you have Docker plugin, you can just run it by one-clicking run service, or you need to execute command like this. And the plugin is here. You can get it from the extensions if you type Docker. Voila. And now what's extra here? So we have also the baseline. So if you want to do comparison, and then MTP if you want to check MTP. And how it looks, we'll see just now. So here you can see the leaderboard that is being computed. And as you can see, I run different configurations. So the lowest one, 15, this is the baseline. So this is the default model that we define. And as we can see, then we have the DFlash model and MTP. And if you notice, most of this DFlash wins. Why? Because as we remember, in MTP, we draft tokens autoregressively, and in DFlash, we use diffusion to basically generate more tokens. And this is the result. And to explain a bit, in the leaderboard, we just run simple prompt for 10 runs. So it's nothing amazing. With separated context, you can play with it. But the goal is to just get a feeling of average tokens. And then there is also acceptance rate. Yeah. So the acceptance rate defines how many tokens from the all drafted tokens are being accepted by percentage. And as you can see, we have the number of runs, the speed. So the difference is quite big. It's around 360 or something like this. But we'll see later the speed tests. I will not dive deep into it. So the most important part is that, as you see, DFlash win. I also do one test with reasoning tokens. So yeah, it takes a bit more. And the interesting part is that for the current implementation, the 15 is the maximum of draft tokens that we can set up here. So if you set more, then the flag will lower it to 15. And MTP, you can go higher, but as you see, you have diminishing returns. So around 8, it performs the best. But it also depends on prompts. So yeah, you could need to test it. So you could ask that these values are low, so why these are not at the top? Because we accept more tokens. But this is the value from total accepted tokens, yeah? So it's not value per verification passed. So even if we accept only 50, let's say on average at 12, then it's still 6 tokens. And here if we accept 80, then it's around 3, 4, yeah? So that's the difference. And all these results that we talk about is saved in leaderboard CSV. And also I use the aiperf. So as we see here, aiperf is a benchmark engine developed by NVIDIA. It looks like this, and you can do profiling of GPUs. This is mainly supported for VLM and SGLang because they are more optimized for the production servers, but we'll use it. And to make it easy, I created 2 scripts. The script with the speed when we define the number of tokens on input and output. So as you can see, maybe I'll make it bigger. So as you can see, it's 512, then number of runs, then 4096, then over 12,000, and then over 36,000. I don't define more because it takes quite a long time for the base model. And the point is that we'll test the base model and the DFlash model. It automatically detects the names from the file and then save it in assets. And for the intelligence, I wanted to try actually the 3 benchmarks, but you need to have specific setups for some of them, and they take a lot of time. My CUDA failed on basically when I ran 2 scripts and crashed the both results. So at the end, I ran just math 500 to see if we actually get similar accuracy as promised. Also important part is that we'll use greedy decoding. So we will choose the argmax basically value because this will allow us for most reproducible results. So greedy decoding means that the temperature is 0, top K is 1, and we do one request at a time with concurrency set to 1, because this is the setup that will benefit local AI, because you don't serve 10 users, you serve yourself. And to specify the output, we basically make it so it will generate tokens after the end of sequence token, but it's details, so I'm not going to it deeply, just so you know. And the second row here, actually that I don't say, is to warm up the model, so the result always makes sense for this context. And in all these runs, I use maximum context, but all the details will be readme in a GitHub repo, and you can run it yourself, check, play with it, and so on. And now you can ask, but you want different model with DFlash. What is supported? zlab collection offer DFlash models. You can check which models are supported here, and what you can always do is, and if you want more models that are not in ZAI, you can always type DFlash here, and then in models, you just choose see all models, and then you can see by sorting which ones you like, maybe most liked ones, and yeah, it's actually Qwen, so that's why we also check it. Quick shout out, there is blog here about it with architecture and also the DFlash paper, and this is the merge that was done. So yeah, big shout out to people who help with it, and there are people having some problems, so I will put this guide at the finish of video with GitHub repo to maybe help some mates out deploying it, because it's pretty cool. And the question was, is it lossless? So I compared both on the same amount of questions and ran both. As we see, the results are nearly identical. There is just one difference in pre-algebra question. I only ran 50 examples because it takes quite some time. But I think this one mistake, we could say it was just the in error range, basically. So that will be basically correcting that we have a lossless speedup. And here we can also see that the difference was just 1% in math 500. And I make mistake before. I changed from 50 to 100 problems. I don't use reasoning because I wanted it to be basically fast. And as you can see, we achieve same results, but the difference in token is 3.75 faster here. And this will all be in results CSV, but this is better way to visualize it. And speed is the interesting one, because as you see here, depending on the context, we get more speed up. It also depends on the prompt because they get generated. And as you can see, there is also hardware. I will go into details soon, but it was on 6000 Pro because that's what I use for tests. And as you see, we have 4.4x difference in token at higher context, which is pretty nice because typically we see that models perform worse with longer context. So this is what I use, my driver version, CUDA version, the graphic cards, this is workstation one, and the CPU, 96 gigabytes of RAM, and AMD Ryzen 9 9950X 16 core. So this will be also all details in the video. So as you see, guys, we go through MTP, all the differences at the beginning, then we added Llama diffusion, and now this is merge of Llama diffusion with basically MTP, which is pretty interesting. So we merge these two technologies to get benefits from both. There is also quad that we mentioned in last quantization video that you can check out. So we'll wait if all these techniques will be added to the models, but from the gains, I think it will happen. So we have lossless speedup, and the gains depends on how we serve it. So as we can see, the peak speedup was in 36,000 token context. This is on input in output, The best config was DFlash 12, but I think this is with the error rate, so I would use 15 anyway. And as we can see, we achieved 256 tokens, and these scores are also from the leaderboard, so from like very small example, and I use 12 in the speed up because I misclick anyway. So and we get the pass of math 500. So the verdict, if you run models locally or serve at low concurrency and your workload is code, math, long reasoning, DFlash is close to free performance. Of course, you need to load the model. That helps with drafters. You can check the size on zlab AI, but it's like, actually, we can check it. Oh, this is DFlash loaded. It takes 26 gigabytes of memory. And now we will look into the base. And this is the baseline, so it's 21. So actually there is difference around 4 gigabytes of VRAM. This is also like in the standby, not wheel computing. So on this page, we can also check the sizes. And as we can see, the 4-bit is 1 GB, then Q5, 5, then Q6, 6, 8, 8, and 16 is 347. There's also, of course, other things that being added to the engine where we run it, but that's the difference to actually, actually gives you guys number of what it oscillates about. So yeah, as I said, DFlash is close to free performance, but the gains are quite big. So especially for speed in local AI, if you use it. So local, low concurrency serving and reasoning models will also benefit a lot. Then if you want high batch production serving and pure freeform chart workloads, we'll need to see how it will turn out. I didn't check it with high concurrency yet, but because we know the theory, we see that we can have an issue with compute. But if this will be fixed by the researchers, then it could be a pretty interesting way to speed up everything. So we can still basically see more growth, like with more pre-trained drafters, or you can train your own speculators, This is also provided. As I mentioned, VLM and SGLang supported it first, so it's very interesting. Okay guys, so if you like video, you could check my other videos when we tested engines, explained MTP, diffusion, quantization, do all of this nice stuff for AI. And leave a comment if you'll use DFlash or not. See you in the next one.